everyone. Welcome to my presentation. My name is Chen Zhang. I am the third year PhD student from the Department of AMS, and I'm doing research on computational applied math now. Before my presentation, I'd like to ask you a question. Suppose we have a lot of gold balls. They are all of the same size. However, one of them is a hollow ball, and all the others are solid ones. So all the balls look the same and only can be distinguished by weight. Then what is the quickest way to find out the hollow one by scales? You can keep it in your mind and think about it, or you may already have your idea. However, at the end of the presentation, you'll have the answer. So today my topic is bisection method, and my presentation will be separated into two parts. First, I will explain this method in mathematics, and second, I will generalize it and show you the application. And I hope all of you could have a good understanding of this method after the presentation. And if you have any questions, I'd like to answer them after I finish. Okay, now let's turn to the definition. It is from Wikipedia. The bisection method in mathematics is a root finding method which repeatedly bisects an interval and then selects a subinterval in which a root must lie for further processing. Looks confusing, right? I'm not going to explain it in mathematics because it's too abstract. So I'd like to explain it by graph. And this is a coordinate system, and the curve represents for a function fx, and this horizontal line is zero line, and when the function curve intersects with the zero line, that point is a root. It's satisfied fx equals 0. So that is what we want to find. So suppose we have such a curve, and at first we know it's in this interval between the two green lines, and we know there's a root because for the two ends, one is above zero line and one is below zero line, and it is continuous. So the curve must intersect with the zero line. So there must be a root. Then the first step, we choose the middle point and see what happens. See the red line. This time it is above zero line. So we know for the right part, one end is above zero line and one end is below zero line. So similarly, we know it must intersect with the zero line. So there must be a root. So next step, we will look into the right part. This time, we choose the middle point in the right part, and again, it is above zero. So similarly, we choose the right part. And next, the middle point is below zero line this time, and so this time we choose the left part. And again, the middle point is below the zero line, so this time we will still choose the left part. And you can see the whole process, we are repeating it again and again, and the whole interval becomes smaller and smaller. So it means when we repeat this process enough times, we can get closer and closer. We can get closer and closer to the exact point. So this is the main idea of this method. And I'd like to show you some features of this method. First, I've mentioned the interval is reduced by half each time. And second, if we try it enough times, we will get as accurate answer, as accurate point as we want. However, the third one is very important because although it's reduced by half each time, it is still very slow. Actually, we have far more rapid methods, but they have more restrictions. And this method has only two restrictions. One is continuous, and one end is below zero, and one is above zero. So very often we use this for the at first and to obtain a rough approximation, and when it meets the requirements for the more rapid methods, we turn to them. So actually, now I will generalize it. We can. I think the most important part of this method is not the mathematical details. It is the main idea here. Actually, the whole process is just these three steps. First, divide the whole thing into two parts, and second, determine which subpath we want. And the third, we look into the chosen part and repeat. So we can apply this main idea into other fields. First, I think CS students may be familiar with this. It is binary search algorithm. In computer science, sometimes we want to search something, search one key in a sorted array, and we use this. First, we can each step we compare the key with the middle element, and if it's exactly matching, then the search is done. And if the search key is less, then we turn to the left path, and if the search key is greater, then we turn to the right path. See this example, if we want to find 4 in this array, first we compare 4 with the middle one, 6. 4 is less, so we turn to the left path, 1, 3, 4. And next we compare 4 with the middle one, 3. And now it's greater, so we turn to the right path of 1, 3, 4. It's exactly 4, so the search is done. Now you may have some idea about the question about gold ball. Yes, we can separate the balls into two paths, and of course the path with the hollow ball should be lighter. So each time we can put them, we can choose the light path and again separate it into two paths, and again we will find it at last. But however, actually there's a better way. The best answer is to separate it into 3 paths. With 2 paths have the same number of balls, and we put them on the 2 sides of the scales, and either side of the other path. And if the scales is balanced, then the hollow ball should be in the 3rd path. And if the scales not balanced, then the hollow ball should be on the light side. So we repeat this, we can find the hollow ball. So do you remember I mentioned in the main idea, I mentioned we separate things into 2 paths. But from this example, we can know the 2 paths is not necessary. Very often we use 2 buttons. in some cases we can use more. Okay, now if you have any questions, I would like to answer them.
Okay, I have a question. Are there any other ways of applying this to real life?
Oh.
Like you said, the thing about computer science, but
Yeah.
are there any other ways to use this? Applications? I don't know.
Very good question, but actually I'm thinking if there's any good example in real life, but at last I can only think of this example. And the main application of this bisection method is here. I said it is used to obtain a rough approximation and then turn to other methods.
In the continuous function, okay, the bisection method can be applied only to the continuous function,
Yeah.
right? But in the discrete function, what kind of restriction is there?
Discontinuous functions.
In discrete, yeah, integer function.
I think I don't think we can use this in discrete function. Can we?
You use binary search in the
Oh.
sorted
No.
algorithm.
Yeah.
That's a discrete function.
Okay. You asked this question because I mentioned this.
Yeah.
But I want to say the bisection method and the binary search only has the same main idea, but they are different things. So bisection method can only be used in continuous functions, and the binary search algorithm is something else. So they are different. So for discrete functions, I don't think bisection method can be used.